Good morning, students. Today we're going to be talking about differentiability from section 2.1. So differentiability is defined as follows. A function is differentiable at x equals c if the graph has a single, very important, numeric, also very important, value of slope at that point. So I'll give you a quick graph here. Let's say that I've got just a regular parabola, and I'm picking, let's say this x value at random here, and let's just say that the slope of the tangent line right there happens to be 2. Now keep in mind, definition of a tangent line is a line that shares the same point and the same slope at that point. So the slope is 2, and you'll notice that 2 is in fact numeric. It is a number. And secondly, there's only one way to draw a tangent line to that original curve, this being f of x, right at that point, x equals 1, just as I have drawn there. And so you have 2 and you have only 2 for slope. And that's where the single term comes in. You have a single numeric value, that is 2 and only 2. We'll take a quick look at a graph, like let's say it's the absolute value graph. And I'm looking for differentiability right at 0. The reason that graph would not be differentiable, rather, at that value of x, is that if I start drawing in tangent lines, I can draw in multiple tangent lines that hit the absolute value of x at a single point. Yet, it's possible to draw multiple of them, so they each have a different numeric value of slope. And so if it's multiple values of slope, then it is no slope at all. Which is why the absolute value graph cannot be, or is not considered to be, differentiable at x equals 0. Now, maybe to make this a little more clear, let's make a list of items where a function would not be differentiable at a given value of x. Let's start off by talking about things that would keep us from finding slope at a given point. Things such as holes. So, for instance, I've got a graph that looks something like this, and I happen to have a hole right here at x equals 1. And it's not possible to draw a line tangent to that curve at that x value because there is no curve at that x value. So the requirement that the tangent line share a point and the slope, those two requirements cannot be met at this value of x. So any sort of a hole in the graph, this, I think it would then make sense that if I also have a vertical asymptote at x equals c, and by the way, this is a hole also at x equals c, it would make sense also that if I have a hole at x equals c, it would be equally hard to sketch a tangent line at a vertical asymptote at x equals c. Thirdly, any sort of jump in the graph would also make it either impossible to draw a tangent line at that value of x, or would enable you to draw multiple tangent lines at that value of x. So for instance, here's a jump in a graph. Let's say that both of these are open circles, and here is my value of c. Another way to look at it would be to fill in one of these endpoints where you've got a jump but a but an actual functional value there at c. The same argument can be made here that you can make with the absolute value. You've got multiple tangent lines through there, each with a different numeric value of slope, making it not rather differentiable at that value of c. The last two conditions have to do with the numeric value of slope, and one we've already talked about with the absolute value. That would be any sort of a sharp turn at x equals c. And it doesn't really need to be that sharp. Any instantaneous change in slope, so for instance, even if you had a function that went from a positive 1 slope to a, I didn't mean to make that, to a 1.5 slope, this point right here would be considered sharp. It's an instantaneous change in slope. So that any sort of a sharp turn at x equals c will make the function not differentiable at that value of c. And then, of course, the last has to do with the numeric value. And if you have a vertical tangent line, the slope of a vertical tangent line is, of course, undefined, that being non-numeric. So a quick picture of that might look something like this, where actually at this value of x, your tangent line has undefined slope. So these are the 5. The most, let's see here, I'd group these together, and these all have to do with continuity. So let's make some room here. Let me get rid of this. The function must be continuous in order to possibly be differentiable. So you must check continuity first. If it fails any one of the 3 steps of the continuity proof, the function will not be differentiable at that x value. Now, if it is continuous, if it does pass the continuity test, you must then go on to the next step. And it's this statement right here. If a function is continuous at x equals c, you must then show that this limit exists. And by the way, this is a two-sided limit. And here is the formula that you must memorize. You've probably already got this thing memorized because you went to school in 5th grade and you took a pre-algebra course. And it is the limit as x approaches c of f of x minus f of c all over x minus c. You can pause this and get this in your notes. But this really is just the slope of a curve at a given point, but it's the slope limit as x approaches c from either side. So it's really just change in y over change in x. And what that ensures is that once you have continuity established, let's say that it's continuous at x equals 1, and the 2 sides are coming together at the same value of y. So this is a finite number. Let's call this 5 here. So the 2 sides are coming together at 5. This limit right here ensures that the slopes also match. So if I have a slope of 1/2 coming in from the right, and I have a slope of 1/2 coming in from the left, that ensures that the curve is nice and smooth there, and I don't have an instantaneous change in slope, or I do not have a sharp turn in the graph. So really, this is nothing more than a smoothness proof after I've established that it's continuous. All right, let's go ahead and work through this example. Let's prove differentiability at x equals 2. All right, just quickly, we'll go through the continuity proof. Step number 1 is f of 2, whether that exists or not. I'm going to use this thing right there. I plug 2 in, and I get the square root of 4, which is 2. Step 2, I got to show that the two-sided limit exists. Limit as x approaches 2 from the right. I'm going to use the bottom. We already know that that's 4. I'll take then the limit as x approaches 2 from the left. I'll use the top curve. So that's 1/2 times 2 plus 1. That also gives me, excuse me, this one right here is incorrect. That's the square root of 4, otherwise known as 2. When I plug 2 into the top curve, I get 1 plus 1. That is also 2, so my two-sided limit exists. And I also screwed up the first one as well. I'm doing an amazing job here. F of 2 is, in fact, 2. So the dot is where the two-sided limit exists. Step 3 then is that f of 2 is equal to the limit as x approaches 2. So it is, in fact, continuous. Now keep in mind, just because a function is continuous does not mean that it's differentiable. I still need to check for smoothness. So let's do that now. All right, so what I'm going to do is I'm going to take the limit as x approaches 2. That's where I'm trying to establish continuity, differentiability. And again, it's going to be f of x minus f of c. So my f of x, as I come in from, in this case, the right-hand side, I'll use the the bottom one, that is root 2x, minus f of 2. And when I take 2 and plug it into, again, that function right there, I get the square root of 4, or 2. And this is going to be x minus my c value, and this is my c value, 2. So the top 2 are y values, bottom 2 are x values. When I plug 2 in, I get 0 over 0, which of course means more work is required. So what I'm going to do is I'm going to multiply by the conjugate, just like we did back in chapter 1. And what I get when I FOIL at the top, I'm going to get 2x minus 4. And on the bottom, I get x minus 2 times root 2x plus 2. I'm going to take a 2 out of the top. And then what I'm going to do is I'm going to cancel the x minus 2's. And then I plug in 2, and I get 2 on the top, and I get 2 plus 2 on the bottom, or 1/2. So I have a slope of 1/2 as I approach 2 from the right-hand side. Now I just want to make some room here. So I'm just going to erase all the work, keep the answer there. What I want to do now is I want to take the limit as x approaches 2 from the left. So my f of x now will be the top curve, 1/2 x plus 1, minus my f of 2, which is 2, all over x minus my c value, which is 2. This gives me 1/2 x minus 1, all over x minus 2. I can multiply top and bottom by 2. It's going to give me x minus 2 all over 2 times x minus 2. These cancel. And I end up getting a limit of 1 on the top and 2 on the bottom. So what I'm seeing here is that the slopes match of 1/2 on either side. So it is differentiable at x equals 2 because it's continuous and it is smooth. I'll look at one more quick example, and it's this one right here. Let's find differentiability at x equals 5 of x minus 5 to the 1/3 power. All right, I'm going to skip the continuity proof. This is continuous. Oh, let's just do it quickly. F of 5 is equal to 0. That's step 1. Step 2, limit as x approaches 5 of f of x. I just take 5 and plug it in. I get 0. 0 equals 0. That's step 3. Check, check, check. This thing is continuous. All right, now I need to check smoothness. So I'm going to take the limit as x approaches 5 from the right-hand side. My f of x is x minus 5 to the 1/3 minus f of 5, which is 0, all over x minus 5. Remember when we take limits, what I'm going to do is, first thing I'm going to do is just plug in 5, and I get 0 over 0, which is indeterminate. So what I'm going to do is now I'm going to cancel. If I have 1/3 on the top and I have 1 on the bottom, I think you would agree that I have 2/3 more on the bottom than I do on the top. So when I reduce that, I subtract them, put the answer where I have more of them. Now, if I just took 5 and plugged this in here, I would get 1 over 0. And if this were a two-sided limit, that would be D and E. Does not exist. But since I'm approaching a vertical asymptote on the slope curve, I will get and I'm coming in from one side, I will get plus and minus infinity. I just need to figure out what this is. So 5.001 minus 5 is a very, very small positive number. To the 2/3 power is still positive. 1 divided by tiny positive is giant. So I get infinity. Now we can already tell that this two-sided limit's not going to exist because I'm getting infinity here. But I'm going to ask you about, on a test or quiz, what this graph actually looks like, and the completion of this limit will tell us what it looks like. So now if I come in from the left, this will be exactly the same, and it will reduce to this again, which is 1 over x minus 5 to the 2/3 power. But now when I plug in 4.9999 minus 5, I get 1 over a very, very, very small negative number. But you got to be careful because I'm taking it to the 2/3 power. So if I third root a negative, it stays negative, but when I square it, it becomes positive. So this is 1 over a very small positive number, and I'm getting, again, infinity. Now you can't have an infinite two-sided limit, but this is telling us something about how the graph behaves, because if I just make a quick sketch of this, I know I'm at 5, 0, and as I come in from the right-hand side, I get positive infinity slope. If I come in from the left-hand side, it's also positive infinity, which means I'm getting something that looks like this. So it is not differentiable, but these limits tell me that I have a vertical tangent line. I hope this makes sense. By the way, you always read slope from left to right, so it's positive infinity to positive infinity. Now, there are other times when you would get something like this. Let's imagine that my limit coming in from the right is positive infinity, but if I take the limit as x approaches 5 from the left-hand side, I end up getting negative infinity. Well, this is what it would look like. If I'm out here at 5, if I come in from the right-hand side, I get positive infinity. So this is very steep, going to less steep. If I come in from the left-hand side, I get negative infinity. So it could look something like this, where it's getting infinitely negative there. But that's not what I want. So it's going to come in from the right-hand side, giving me negative infinity, creating a sharp point. Still not differentiable, because the two-sided limit does not exist. So to sum this up, if you have mismatched infinities, it's always a sharp point. If I have matching infinities, it's always a vertical tangent line. I hope this is clear. Come see me if not. One quick closing joke. You know what's extremely dangerous and swings from trees? That's right, a chimp with a machine gun. Have a wonderful day.